Today we're going to talk about catalysts. Please turn in your packet to the very bottom of page 4 where it says how do catalysts operate. You might have heard a little bit about catalysts before. It's definitely not an unfamiliar word. Catalysts are substances that increase the rate of a reaction by providing an alternate pathway for the reaction to occur. This pathway is usually a little bit easier, requires less energy, and might even let the reaction happen at a lower temperature. What is important to remember about catalysts is that they are not used up during the reaction. When a catalyst is used, it's going to reduce the activation energy, or the energy of the activated complex, but nothing else. It will not affect the energy of the products, it will not affect the energy of the reactants, and it will not affect the delta H. It's basically an energy shortcut. Say, for example, you wanted to drive from school to Walmart. You would drive along Hollow Hill Road, and as you were going along, you would have the opportunity to maybe take Corporal Welch Road, but you could also go all the way up to Casson and then continuing your route right over to Walmart. If you were in a real hurry to get to Walmart, however, most of you would end up taking Corporal Welch Road. That's a shortcut. So the normal path involves going up and around like this. This is a shorter route. This is essentially what a catalyst does to a potential energy diagram. Simply makes a shortcut. Where you start is the same, and where you end up is the same. It's just a little change in your path. So again, remember, you're starting at the same place and ending up the same place, just shortening your route a little bit. On a potential energy diagram, you should be able to show the effect of a catalyst. What a catalyst is going to do is simply cut off the very, very end of this strip and just make a simple little shortcut. So now the reaction doesn't have to go up quite as high all the way to 100. It would only have to go to maybe 85 or so. So what this did for us was it changed our activation energy. If our original activation energy, we were going from 60 up to 100, if our original activation energy was 40, our activation energy now, if we're going up from about 60 to 85, is now only going to be 25. That's less energy. However, it's important to note, we started in the same place, we ended in the same place, and our delta H in this reaction is still going to be the same. It's still going to be 20 minus 60, or negative 40. There are a lot of different examples of catalysts in our day-to-day life. You have a catalytic converter in your car. This is a honeycomb surface, as you can see right here. On that honeycomb surface, it's a porous substance that allows reacting molecules to have a lot of surface area for reactions to occur. You learned last year in biology about enzymes. These are biologically active catalysts. Many enzymes work by the lock and key model. If you want to have a bond broken in a reactant, it might slide into an enzyme like this, and then that enzyme holds it there so that that bond can get broken, and you can have two separated molecules at the end. A similar thing can be done to actually hold molecules together and allow them to bond. This is another diagram of a porous substance that might allow different atoms or molecules to sit on it and be held in place while they have the ability to react with one another. One common place where catalysts have been really important is the development of fuel cells. Hydrogen fuel cells could potentially be a way to power cars in the future that give off water as exhaust. They do require a platinum catalyst where molecules and reacting substrates are able to sit kind of on this catalyst surface right here until they have the ability to react with one another. So basically it holds them into place. This makes it easier for the reaction to occur. You should be able to draw the effect of a catalyst on any type of a reaction. Every time you're going to simply just cut off the very, very top, give yourself a little shortcut to the ending of your reaction. Keep in mind, catalysts are like a shortcut. Delta H remains the same, potential energy of the products remains the same, and the potential energy of the reactants remains the same. Reactions also have the ability to run in reverse. One example of this is the reaction of nitrogen and hydrogen to form ammonia. This is right on the top of page 6, so please flip your page to page 6 if you have not done so already. Some reactions, such as this reaction, could run in the direction where N2 and O2, or I'm sorry, N2 and H2 react to form ammonia. This reaction can also run in reverse, where NH3 is decomposing back to the elements from which it came. This can be shown in the reaction right on the top of your sheet. In this reaction, the forward reaction would be considered to be the reaction of NH3 and H2. The forward reaction in this case is going to be considered exothermic because it ends lower. The reverse reaction is the decomposition of ammonia back into the elements it came from. What you are expected to be able to do is read a potential energy diagram for both forward and reverse reactions. Reading a potential energy diagram for a forward reaction is pretty straightforward and exactly like what we've done. We're starting with 10, ending with 15. Our activated complex has a potential energy of 30. Our delta H in this case is 15 minus 10, or positive 5. And our forward reaction in this case is endothermic. Our activation energy for our forward reaction is going to be 20 because we're going from 10 up to 30. For our reverse reaction, this is now going to be our reactant. We are running this simply in reverse. So our energy of our reactants now would be 15. Energy of our products is where we end up, or 10. Potential energy of our activated complex is 30 no matter which direction you're going in. That's the highest place you got to get to. For our delta H, because we've flip-flopped our heat of our product and our heat of our reactant, instead of doing what we did in the last one, we're just reversing our numbers. So now this is going to be 10 minus 15, or negative 5. We're also going to end at a lower energy, and our delta H is agreeing with this. We have an exothermic reaction. Finally, our activation energy, we're starting with 15. We got to get up to 30, so we have to put in 15 kilojoules of energy. Please take a moment, look at the bottom diagram, determine if the forward and reverse reactions are exothermic or endothermic, and complete each of those simply using the letters because you don't have numerical values given.